what is special about fields? So we have understood the abstract structure group. So we have seen modular arithmetic of Z5 under addition and multiplication group. So in the specification, SE326 K1 specification, there is this term used, a finite field FP over this P, which is a very large prime number. Okay. So what is a field? The definition, the easiest definition that I can give you is a set, right? A set F, since it's a field, we are denoting the set as F, is said to be a field if F is a group under addition and a group under multiplication. Of course, when we talk about multiplication, we ignore the element 0. Okay, for the same reason, right? So when we are studying Z5 under addition, we included from 0, 1, 2, 3 and 4. But when we talk about multiplication, Z5 under multiplication, we excluded 0 because it does not have the multiplicative inverse. Whether Z5 is a field? Yes, because Z5 is a group under addition and it is also a group under multiplication. So why this property of field is important? Because in the way this elliptic curve addition is defined, we will see how elliptic curve addition works. And the signature schemes, ECDSA and Schnorr signature scheme, whatnot. For all of those things, the computations, we need both addition and multiplication to be defined. Then only we can have a meaningful cryptographic structure. And if you are sure enough, right, so we require this P to be a prime. If P is not a prime, 5 is a prime number. That's why it is this Z5 is actually a field. If 5 is, if this N, right, the P, whatever, it is not a prime. Let's consider Z6, 0, 1, 2, 3, 4, 5. You can easily verify that under addition, Z6 is a group. Under multiplication, right, so Z6 under multiplication, we does not include the 0, right? We just include 1, 2, 3, 4 and 5. Whether this forms a group, if it has to form a group, of course, you can verify the closure and associative properties that will satisfy under multiplication as well. The identity element 1 is there. If you multiply anything with 1, you will get the same number. But you can easily find out that not all the elements have the inverse, multiplicative inverse. Okay, let's check. For 2, right? So 2 to the power x, we check all the powers of 2 under multiplication. So we have 2, 4, 8. We are taking modulo 6. So remainder 2. Okay, and 4, 8. We are already encountered a cycle, right? So 2 to the power x is just the set 2 and 4. We never encountered the term 1. Okay, so no matter what we multiply 2 with, we will never get the inverse. You can verify that. 2 times 3 is 6, which is 0. 2 times 4 is 8, which is 2. 2 times 5 is 10, which is again 4. So this 2 has no multiplicative inverse. If you remember in Z5, 4 is not a generator. Okay, it did not generate all the group, but it is a multiplicative. It has an inverse because 4 into 4 is 16. And when we are taking modulo 5, this is 1. Here we are talking about modulo 5. Okay, I'm recalling from the previous video presentation. So Z5 is a field, but Z6 is not a field. The reason is simply 6 is not a prime number, not a prime. I'm not going to give the mathematical proof. I'm not going to cover that mathematical proof in this course, but I hope this helps you gain more understanding.